Good evening, students. Welcome back to one more session of your World of Chemistry, that is your mind maps. So recently, I think 2 days before, I have kept in the community tab, I said, students, please vote. What do you want? I said I've given an option of hydrogen, redox reactions, mind map and grade 10 syllabus. So maximum votes were, I think you have all voted for mind mapping. So I've decided to go with all the mind maps of grade 12. Right. So in this grade 12, all the 16 chapters will be covered from my side. But one thing you need to promise me, students, unless until you watch the video, unless until it is shared with your friends, I can't go further. I expect more and more number of students to watch this. Because of your, let it be your JEE exam, let it be your NEET exam, let it be any sort of competitive exam, this particular mind mapping from NCERT, completely 100% from the NCERT, every word is taken up in this. So I have prepared a template. So let's start off with the first chapter, that is solid state. I'll be uploading the video for all the 16 chapters. My request is you need to watch it on regular basis and make this a huge success, students. So let's start off. So whenever I take or speak about solid state, first of all, solid state, let us see what we have. We have classification, isn't it? So in your first chapter in NCERT, basically solid state, one side we have classification and the other side we have a topic called crystal lattice. So when we speak about the classification of solid state, how many classes it is divided into? It is divided into amorphous solids, right? And the second category is crystalline solids, isn't it? Done. So what are amorphous solids basically? Amorphous solids are those in which the particles have irregular shape, correct? So I will not write the full definition, I will write irregular shape. So particles have here irregular shape. Done. That is the first thing about this. When I come to crystalline solids, most important thing, as I have said, the quite opposite here. If it is irregular shape, here in crystalline solids it is the particles are arranged in a regular shape. That is an important thing. Done, the students. Now crystalline solids, again they are of large number, and these are again divided into 1, 2, 3, 4 varieties. So the first variety, if I have to take, let us start from here. Here the first variety which is divided is nothing but molecular solids. So if I have to write, the first variety of classification of crystalline solids is molecular solids. So molecular solids are again further divided into 1, 2 and 3 variety. The first variety of the molecular solids is nothing but non-polar solids. Okay. The second category of the molecular solids are polar solids. Done. The third category of molecular solids are hydrogen bonded solids. Done. Further, after molecular solids, there is one more classification of crystalline solids, that is nothing but ionic solids. Ionic solids. Let us come back and write the definition later. The next category of crystalline solids which it is divided into is, after molecular, after ionic, next comes covalent solids. After covalent solids, there is one more category of crystalline solids, that is nothing but metallic solids. Easy, students? Done. So classification, it's divided into amorphous solids which have irregular shape, crystalline solids which have regular shape, as well as it is again further divided into molecular, ionic, covalent and metallic. Further, molecular solids are again divided into non-polar, polar and hydrogen bonded. So when I have to speak about the molecular solids, right, let us see the definition. I'll just tell you the definition, you can note it because the place is very less. I'll write the examples. So whenever we speak about molecular solids, and that too, which is a classification of the crystalline solids, you need to remember that here in molecular solids, what are the constituent particles? Nothing but molecules. So you can write in your books, molecular solids are those compounds in which molecules held by intermolecular forces. Means all the molecules are held tight together by intermolecular forces. If I have to take an example, methane is one example, glucose is one more example. Right? So molecular solids, what are they for? Particles arranged, that is molecules which hold the crystal lattice together by intermolecular forces. Now When it comes to non-polar solids, here what are the constituent particles? In non-polar, it can be atoms or molecules, right? But what are the forces which are acting? So atoms and molecules are held by weak dispersion forces or London forces, remember. So I'm writing the forces here. In non-polar solids, London forces or dispersion forces will be acting. So what is the best example of this? Argon and helium. Done. When it comes to polar solids, here molecules, here we said atoms and molecules, it can be atoms or molecules which can be held by dispersion forces. In case of polar, molecules will be held together by which forces? The forces which are acting are dipole forces. So dipole forces will be acting in this. If I have to take an example, sulfur dioxide, HCl, or one more example. Suppose if I am talking about hydrogen bonded, here molecules again, here molecules are held together by which bonding? Hydrogen bonding. As the name suggests, they are held together by hydrogen bonding. Right students? Done. So here the example is water, nothing but ice. Simple, isn't it? So let us come back. In crystalline solids, solids are classified into amorphous solids and crystalline solids. Crystalline solids are again divided into molecular solids, ionic, covalent and metallic. Molecular solids are again further divided into non-polar, polar and hydrogen bonded. Done. Now let us come back to ionic solids. In ionic solids, what is that speciality? Here basically ionic solids, as the name suggests, ions only are the constituent particles. So ions are held by what? They are held by strong Coulombic, spelling little bit COULUMBIC, strong Coulombic forces. So if I have to take the example of this common thing, NaCl is one example, MgO is one more example. Yes students? Done. So here the ions are held by strong Coulombic forces. Now when it comes to covalent bonding, in covalent bonding we basically talk about non-metals. Here non-metals, what are they held with? They held with covalent bond. So non-metals are held by covalent bond. So give me some examples of covalent bond compounds. Covalent bond. So covalent bond, when I have to take, the examples are, best examples are silicon carbide. Yes students, silicon carbide, carbon is one more example. So when I take the last classification of metallic solids, as the name suggests, here in metallic solids, the metal atoms are held by which bond? Metallic bond. So I am writing metallic atoms by which bond? Metallic bond. MB I am writing, metallic bond. So examples are, you can take any metal, iron, copper, like that, any metals you can write. So this is how, this is the most important thing which you need to remember. You need to remember the name of the solid, as well as you need to remember what is the type of force acting in that. Right students? Right students, now after this classification, let's come back to the basic unit of the solid state, that is we speak in terms of crystal lattice, isn't it? So the packing of the solids is in what? Basically they are packed in the form of a crystal lattice. Now crystal lattice, what is the smallest unit? If I have to write in crystal lattice, I am using a black pen now. I think it is clearly visible. So in crystal lattice, the smallest unit is nothing but unit cell. Yes, so here in unit cell, we are going to calculate the density also. We are also going to see the types of unit cells, correct? Yes. So when to calculate the density of the unit cell, the formula which we use, so density in this way is equal to Z capital M by A cube Na, right? So this is a formula which we are going to use directly. You may be given one quantity, this one may be missing, you need to calculate remaining. This is given, you need to prove that density is so much, like that different variations will be given to each, right? So Na is the Avogadro number. Done. So here again in unit cell, they are classified into primitive unit cells and centered. So this first category here would be primitive, PRIMITIVE, primitive unit cell is one category. The second category is nothing but centered unit cells, right? So primitive unit cells are those where, what is this here? Particles are only at the corner positions. In primitive, all the particles are at the corner, but here in centered, we have again three varieties that we'll be writing very soon. First we'll finish this. So in unit cell, in primitive, what should you remember? Particles are only on corner position, only on corner position. This is the concept, right? So here when I have to speak, we have different types, that is we call the Grievious lattices. There are 1, 2, 3, 4, 5, 6, 7 varieties of Grievious lattices. So the first variety which you should remember is cubic. Correct. So in cubic you need to remember the bond angles, that is the edge lengths, that is alpha, beta and gamma. Here what is the important speciality of cubic? Here basically alpha is equal to beta is equal to gamma is equal to 90 degrees. This is done, isn't it? Now if I have to see the example of cubic lattice, sodium chloride is example, polonium is example, copper is example of cubic crystal lattice. Done? Yes. Next thing, next is a tetragonal structure. So when I go with the tetragonal Grievious lattices, what is the thing? This is also primitive in nature, as you have written here. Alpha is equal to beta is equal to gamma is equal to 90 degrees. Right? Here examples would be tin, SnO2, TiO2. The next category is the orthorhombic variety of Grievious lattices. In this, A is not equal to B is not equal to C. In other terms, alpha, beta, gamma is equal to 90 degrees, but the edge length A is not equal to B is equal to not equal to C. Here in this case, everywhere it is 90, but here what is the thing? A is equal to B is not equal to C in case of tetragonal. In case of cubic, when we write A is equal to B is equal to C. Done, students. Now orthorhombic, when I have to give example, gallium is one example, barium sulfate is one example, potassium nitrate is one example. The next category here is, now here again ma'am, what is alpha, beta, gamma? Here alpha, beta, gamma is the same as above, exactly the same. Alpha is equal to beta is equal to gamma, 90 degrees. Now when we come to the next variety, that is a hexagonal type of Grievious lattices. So in hexagonal, again here A is equal to B, which is not equal to C. So again here angles, when bond angles, when we write, alpha is equal to beta, which is 90 degree, and gamma is 120 degree. Yes students, done. Next comes rhombohedral. So in rhombohedral, the other name rhombohedral is the triclinic, isn't it? So in rhombohedral, when we take the examples are tin, mercuric sulfide, calcium carbonate, right? Here A is equal to B is equal to C, and when it comes to the angles, that is alpha, beta, gamma, all three equal to 90 degrees, right? So next comes monoclinic. So when I write the monoclinic Grievious lattices, so what should you remember? Example is sulfur, yes, polonium, yeah. Now here alpha is equal to gamma is equal to 90 degrees and beta is not equal to 90 degrees, right students? So it is again primitive type of Grievious lattice. Last is the triclinic. So in triclinic, potassium chromate, boric acid is one example. Here A is not equal to B is not equal to C, and alpha is not equal to beta, which is not equal to gamma to 90 degrees. So these are the 7 Grievious systems which we have. The bond parameters means the edge lengths also are given, or the angles between the edges also are given, alpha, beta and gamma. So 1, 2, 3, 4, 5, 6, 7. I repeat the examples again for your students. Cubic, you can take the example of sodium chloride and polonium. Tetragonal, you can take an example of tin and titanium oxide. For orthorhombic, you can take an example of potassium nitrate and barium sulfate. For hexagonal, you can take an example of zinc oxide and carbon monoxide. For rhombohedral, you can take an example of calcium carbonate. Done. For monoclinic, you can take an example of polonium and monoclinic sulfur, sodium sulfate. For triclinic, you can take an example of potassium dichromate as well as boric acid. Done? Yes. Now when it comes to centered, here it's again of 3 types. One is BCC, one is FCC, one is ECC. So in BCC, what you should remember, basically one particle is at the body center and at its corners in face centered, one particle at the center of each face and its corners. Means here you have at the body center and the corners. In face centered you have one particle in the center of each face as well as corner, and in end centered one particle at the center of any two opposite faces, up and down. Suppose if I take this one, if I have to draw like this, in end centered you will have one opposite here, one more like that. So in BCC, when I have to speak about, right students, so remember the number of particles in each, in BCC, FCC and ECC is what you have to remember. Right, so now let us see the centered unit cell. As I said, there are three varieties, that is BCC, FCC and ECC. So BCC stands for body centered cubic lattice, face centered cubic lattice as well as end centered cubic lattice. Right, so here basically when I have to speak about further things, if I have to add, you can also write cubic unit cell, all these unit cells in these. Further I can also write simplest unit cell is one more category. You can also write HCP, hexagonal packing also, so HCP. So let us see the important thing which you have to remember. So here when I have to speak BCC, you need to remember two things. That is, in BCC what happens, so basically in BCC the atoms, as I said, one particle at the body center and all the corners. So here the coordination number for BCC is 8 and the number of atoms number is 2. Coordination is 8, number of atoms is 2. In face centered, the coordination number is 12 and the number of atoms are 4. In ECC, the number of atoms is 2. Right. In simplest unit cell, the coordination number is 6 as well as the number of atoms is 1. When I have to speak about HCP, the coordination number here is 12 and the number of atoms here is 6 per unit cell. Hope this is clear, students. Done. So this is the classification of the solids, crystalline and amorphous, both we have written, and after that we have seen the crystal lattice, in which the smallest unit is a unit cell. Unit cell is again we are going to calculate the density of it. Further, unit cell is again divided into primitive and centered. Primitive is again divided into 7 Grievious lattices and centered is divided into BCC, FCC, ECC and 2 more I have mentioned down. Now let us see the next part of the mind mapping. When I have to speak about solid state, same thing. Packing efficiency is where you have to remember, and next would be voids. So these two topics I have taken in one sheet. So when I have to speak about the packing efficiency, let us see the types. You have SCP, square close packing, HCP, hexagonal, then you have CCP, yes, and you also have BCC. Here the arrangement of the atoms when I have to take the square packing, so you have AAA type which will be repeated. So AA type would be this. What is the packing efficiency here? It is nothing but 52.4%. Correct. Here the example is polonium. When I have to take the HCP packing, here the packing is AB type. AB type. So here the packing efficiency, the percentage is 74%. So zinc is one of the best example. When I have to speak about CCP, here the packing is ABC type of packing. ABC type of packing, where the packing efficiency is again 74%. If I have to take an example, silver, copper is the best example. When I have to speak about BCC packing, here it's nothing but square close packing. So in BCC the type of packing is square close packing. What is the packing efficiency here? 68% is the packing efficiency. So example is lithium and sodium. Done, students. Now when I have to speak about voids, what are voids? Basically the gaps in between, isn't it? Right. So voids are, again, when I have to study clearly, if I have to see the definition, we have to write these are the empty space between spheres. Let us write that. Voids are empty space between spheres. Correct? Yes. So now these voids are further divided into how many varieties? First would be the trigonal type of void. Next would be tetrahedral type of void. Tetrahedral type of void. Next category would be octahedral type of void. So trigonal type of void, what will happen here? Tri means 3. 3 spheres are in contact. Correct? So let us write 3 spheres are in contact. 3 spheres are in contact. Okay? Trigonal. Here contact. Here what is the radius ranging between? It's going to range between in trigonal 0.155 to 0.225 in trigonal. So when it comes to tetrahedral, here tetra means 4. 4 spheres are in contact. 4 spheres are in contact. So here what is the radius range? It is nothing between 0.225 to 0.414. When it comes to octahedral, as the name suggests, octa 6. So 6 spheres in chemistry we call octa 6, isn't it? 6 spheres at the vertices of the octahedron. When you take the octahedron, I did a video also for this. So there are 6 spheres present. What is the radius here? It ranges between 0.414 to 0.732. Right, students? So this is clear, I think. So solid state, packing efficiency, you need to remember this, and the type also, as well as voids, that is the empty spaces, which are divided into trigonal, tetrahedral and octahedral. Again further, you need to remember the range. Right, so after this study, let us come back to next important concept of the solid state. You have to remember, that is the magnetic property as well as the electrical property. Right, students? Then we will do the defects. Right, so when I have to speak about the electrical property of solids, so basically electrical properties, we are going to study under 3 categories. That is, first category is the conductors, next category is the insulators, next category is the semiconductors. Correct, students? Yes. So electrical property, we are further going to study under 3 categories. As I said, conductors, insulators and semiconductors. So again, further semiconductors are again classified into, as I have written one more classification here, the semiconductors are again divided into N-type semiconductors as well as P-type semiconductors. Done. So where we have to, what should we remember in conductors? So basically conductors are those substances, important thing in this. You have 2 bands, isn't it? One is the conduction band and the valence band. So in conductors, what is important? The overlapping or the gap between conduction and the valence band is very small. So let us write gap between conduction band and valence band is very small. If I have to take the examples of the conductors, aluminium wires, aluminium basically, yes, so it conducts current, that's why we are using it in the form of wires. Copper, yes. So when I have to speak about insulators, the same concept, the gap between the conduction and the valence band, this is very small. This is a bit, means the gap, you can observe it clearly in the insulators between the conduction band and valence band. Gap between conduction band and valence band. When I have to take the examples of insulators, clay, best example is clay, I believe I can give. Yes. Next comes semiconductors. So what are semiconductors? Basically there is very large gap compared to this, very large gap between conduction band CB and valence band VB. So silicon and germanium, we remember group 13, 14, 15, we start doping them, then we get 2 varieties of semiconductors. So in N-type semiconductors, that is nothing but the negative charge, in this case negative charge, and in P-type positive charge. Yes, students, right? So here in the negative charge, so how does it look? One atom, gap, electrons, gap, electrons, gap, electrons. So in this way, if it is drawn in this sequence, so arsenic in the center. So I did one detailed video about this also. You can watch the p-type and n-type. Now when I take the positive charge, so arsenic here, we are doped in where? In p-type, electron. Okay. Boron, I have, sorry, boron. Yes. So boron, you very well know what is atomic number? 5. So 13th group, and this is the 15th group which we are doping it. So for clear understanding, please watch the p-type and n-type video in World of Chemistry. It is available there. Next comes the magnetic properties. So when we are studying magnetic properties, we are going to study under 5 different categories. That is paramagnetic behavior of that is one of the category of magnetism. Next would be diamagnetic in nature. Next would be ferromagnetic in nature. Next would be antiferromagnetic in nature. Next would be ferrimagnetic in nature. Ferrimagnetic in nature. Magnetic. So when I have to speak about paramagnetic, let me give you the definitions. You can note, students. So paramagnetic means weakly attracted. Means unpaired electrons here. So important thing is it is weakly attracted, and what you have? Unpaired electrons. Unpaired electrons. In diamagnetic, weakly repelled. WR means weakly repelled. Here you have paired electrons. Paired electrons. In ferromagnetic, strongly attracted. Strongly attracted, and all the domains are in same direction. So all will be in same direction in this way. All the domains. In ferromagnetic, domains are opposite. If 2 domains are up, 2 will be down. In this way, equal domains, but opposite. In ferromagnetics, domains are unequal. Domains are unequal. Unequal means if 3 are up, 2 may be down, and 3 like that. They are unequal. So WA stands for weakly attracted. I am writing full form. WR stands for weakly repelled. SA stands for strongly attracted. Yes, students, strongly attracted. Done. So when I have to take the example of paramagnetic, oxygen is one example, copper is one example. Diamagnetic, if I have to take, all are paired electrons, where I can take an example of water. So when I have to speak about ferromagnetic, where all the domains are in one direction, the same direction. Iron is example, strongly attracted. So when it comes to antiferromagnetic, as I said, the domains are in the opposite direction, they're equal. Manganese, MnO. Manganese oxide is the best example. So when I take ferrimagnetic, domains are not equal, I said. Fe3O4 is the best example. Fe3O4 is an example. Right, students? So this is about your electrical property as well as magnetic property. Now let's come back and do the last, that is the defects of solids. Very important topic. So when I have to start with the defects or the imperfections of solids, how many types of defects we have? We have both the point defects as well as line defects. Yes, students? Yes. So when I have to speak about the point defects, point defects means where you will find the defect at one point. Means basically we are talking about at a point. Line defects are what? They are going to show it in entire row. Done. So point defects are further they are classified, means they are also called as stoichiometric, means stoichiometric defect means they will not disturb, they will disturb, both are there. So we will speak in terms of stoichiometry, the exact ratio of this. So if they disturb, suppose if the stoichiometry ratio, if there is imbalance in the ratio of the crystal lattice, if it disturbs, there are again two varieties. If the stoichiometry does not disturb, so stoichio STOI CHOMETRAC, stoichiometry. If the stoichiometry do not, then the type of vacancy is called, the type of defect is called vacancy defect. Vacancy defect. Once again, if the stoichiometric ratio, if it does not get disturbed, then it is called vacancy defect. So only the lattice sites will be vacant. Here in vacancy defect, when the lattice sites will be vacant, so in what it is observed? It is observed in ionic solids. So only the vacancy will be created in the lattice sites, or the vacant lattices will be there. Suppose if the stoichiometry is disturbed, then here do not disturb is vacancy. This I have written. If the stoichiometry is disturbed, then you have to remember it is an interstitial defect. Interstitial defect. So here what is happening? Here we said only the vacancy is created in the lattice sites. But here in the interstitial defect, the particles whatever are there in the lattice side, they'll go and occupy in the interstitial space. Means when it is fixed like this, one of the particle will go and occupy the interstitial space. So this is also observed in non-ionic solids. So remember students, stoichiometry, again we have stoichiometry not disturbed is vacancy, stoichiometry disturbed is interstitial. Now let us come back to line defect. So line defects, here we said there is a defect in the entire row. Again these are classified into two varieties: non-stoichiometric, this is non-stoichiometric defect, and this is the impurity defect. Impurity defect. So when I have to speak about the non-stoichiometric defect, it is again of two types. What do they do in non-stoichiometry? They disturb the stoichiometry. Basically, non-stoichiometry means they disturb the stoichiometry. It is again of two varieties, that is metal excess defect and metal deficiency defect. Metal excess defect and metal deficiency defect. So here in metal excess defect, what happens? Why? Due to anionic vacancy. This is why it is created, due to anionic vacancies and presence of extra cation. So let us write two keywords: due to anionic vacancy and presence of extra cation. Done. Example is zinc oxide for this metal excess defect. So in metal deficiency defect, what happens? It shows variable valencies. The best example which we take is Fe+2, Fe+3. So metal deficiency defect is due to variable valencies. Let me come back and repeat. Metal excess defect is due to anion vacancy which is created, as well as an extra cation comes and occupies its space. And in metal deficiency defect, as Fe+2 and +3, iron shows two oxidation states here, so it shows variable valency. Because of that also metal deficiency defect. Next comes impurity defect. Impurity defect are of two types. One is Frenkel defect as well as one is Schottky defect. So in Frenkel defect, what is happening here? Smaller ions are dislocated to interstitial sites, smaller ions. And here, okay, let us write smaller ions, that is the cations, are dislocated. Smaller ions are dislocated. In Schottky, what will happen? Equal number of ions are missing. Equal number of ions are missing. Right, students? So in Frenkel defect, what is the example? Zinc sulfide, silver chloride is an example. In Schottky defect, as I said, equal number, both the cation and anion. Best example, sodium chloride. Potassium chloride is an example. Right, students, so this is the complete summary of the solid state chapter from my side. Let us see what we have learned in all the papers. Let me get all the papers. Yes, so let us see the whole thing once again. So I have taught in the first page, students, this is the thing. I have taught about classification into crystalline, as well as we have studied about the crystal lattice, unit cell, primitive type and centered type. Again, in classification, I have taught you about molecular solids, ionic solids, covalent and metallic. Further classification of molecular solids. In page 2, I have taught you what is the concept of the packing efficiency, what you should remember for your exam, and voids. Right, after that I have also taught you the solid state, that is in solid state electrical properties and magnetic properties. Here we have studied electrical properties under conductors, insulators and semiconductors. Semiconductors are again divided into N type and P type. In magnetic property we have studied the important thing to remember: paramagnetic, diamagnetic, ferromagnetic, antiferro, as well as ferri. In that, which is strictly attracted, which is strongly attracted, which is repelled, I have written here. Examples also I have given. Next, in last category, I have given the concept of the defects or the imperfections. They are classified into point defects and line defects. Again, we have given stoichiometry, where there is no stoichiometry which do not disturb. Stoichiometry is not disturbed, that is vacancy. Stoichiometry is disturbed, that is interstitial. As I also gave the definition of the interstitial also, you can watch little bit, go to the previous this one and pause and listen to it. Again, line defects are divided into non-stoichiometry, that is the disturbance of the stoichiometry, metal excess and metal deficiency, and impurity defect, Frenkel and Schottky. So this is the thing, students. Thank you for watching. I'll also meet you again with the next chapter, that is this time it will be one organic chapter from my side. After that I'll be doing one physical, one organic, one inorganic. Like that I'll be doing all the chapters. All the 16 chapters will be done from my side. Thank you for watching. Stay happy. I expect most of the students to watch this completely and share it with your friends. Stay happy, stay healthy.